Okay, so let's start. Last lecture, we were looking at this particular diagram here. We were looking at this energy diagram which shows the conduction band edge, the valence band edge, the intrinsic level here in the middle, and it shows the Fermi energy. And we said that there are a number of interesting things that we can determine from this energy band diagram. The first one of them was, we said, when we look at the diagram like this here and we see EF is constant throughout, what it tells us is that the device is in equilibrium, right? That's the first thing that we note here. The second thing we note here is that the material EF is above EI, above intrinsic level here, throughout the material here, and EF greater than EI. Remember, N equal to Ni, e to the power EF minus EI divided by KT. That's one expression for current here, for electron density, and therefore we can say that the electron density is larger than Ni throughout this particular system here. So EF above EI denotes that electron density is larger than intrinsic carrier concentration, and therefore the whole material is N-type. It's not P-type. And we also note that the electron density is non-uniform. The difference between EF and EI is larger here, so we expect more electron concentration here. Another way of looking at it is that the energy separation between EC and EF is smaller here. So EF is closer to EC, so I have more electrons here and lesser here. So electron density is non-uniform, higher here and then decreasing as we go towards the left here. And since we have given you the EC here and the separation between EC and EF, and similarly you have a separation between EF and EI, so you can actually get what is N0x. So you can get the whole profile of N0x, because remember, N0 is nothing but Ni multiplied by exponential of separation between EF and EI. So we know all the terms and we can get how N0 varies as a function of x here. And what you would note, what you would see here, if you do it, you would find that N0 is decreasing exponentially. Okay, because it's an exponential function of energy difference here, and the energy difference is increasing linearly, and therefore the electron density would decrease exponentially here. Potential is directly related to, we said psi equal to minus EC by Q, so it's related to EC here, so we know potential here. Potential everywhere in the system. So choosing a particular reference, and from that reference we can find out where what the potential is anywhere inside my device here. And obviously once I know the potential, I know the electric field as well. And electric field, we can see here, electric field is pointing in this particular direction here. Okay, and once you know the N0x, then you know the diffusion current, you know its direction, and you can even calculate its magnitude. And once you know the electric field and you know N0x also, you know the drift current as well. Similarly, because the system is in equilibrium, once you know N0x, you know P0x as well. N0 P0 is Ni square, and therefore you know this value also. The other way of saying is, once you know the difference between EF and EI, you know P0 also. P0 also depends on the same difference here. And therefore we can obtain the whole current components also. Once you know P0x, once you know electric field, so you know drift, diffusion currents. And vacuum level, we said vacuum level is the difference between the vacuum level and the EC is equal to electron affinity. We'll talk more about the vacuum level today. And so therefore, if you want to draw E0 vacuum level, all you need to do is go above EC by the electron affinity and just draw it out. Okay, so the separation between vacuum level and EC is always fixed at electron affinity. As I said, we'll talk a little bit more about vacuum level in a minute here. All right, so this was one very simple energy band diagram. Let's look at this particular diagram. So it shows EC. All right, it shows EC, it shows EV here, and it shows EF. Right? I've not drawn EI, intrinsic level, but you can easily draw where does intrinsic level lie? In the middle, right? Between EC and EV. So all you have to do is draw something in the middle like this, and it will go here. All right, so what can we see from this diagram? What all can we conclude? Given a diagram like this, what all can we say? EF is constant throughout, so we know it's equilibrium. What else? Look at the diagram here. See, EF is very close to EC, right? EF very close to EC means what? N-type. N-type meaning lot of electrons. And EF is very far from EV, very few holes. So here is a material which is rich in electrons, very high concentration of electrons, very little holes here. So it's an N-type. When I go on the other side, it's very close to the valence band here. And very close to the valence band means that the material has a lot of holes here, very little electrons here. So what is this system then? There's a P here and there's an N here, so it's a PN junction, right? It's a PN junction that we can see here. What else can we get from here? What else can we get from this diagram? So we recognize that it's a N region here, it's a P region here. What else can I get from this particular diagram now? What does this variation tell us? This change in EC starting from here. What is the electric field here at this point? Electric field is what? Derivative of the conduction band edge, right? Or derivative of EV. So electric field is 0 here, right? Electric field is 0 also. What is the direction of electric field here? Electric field is what? 1 over Q, derivative of EC with respect to X. So derivative is negative, right? So it's going left. It's going from right to left here. That's the direction of electric field here, right? That's the direction of electric field pointing from left to right here. What does this variation actually tell us? So there is an electric field, but this, so if I take a point here and I take a point here, right? The difference between the EC of these 2 points will represent what? Because potential is what? Keep in mind, potential psi equal to minus EC by Q plus some constant, some reference. So the difference between EC here and the difference between EC here will tell you what is the potential difference between these 2 points here. And note, the diagram has an energy scale attached to it. So I know what is the EC value here. Whatever is the EC value I can read. I can read the EC value here. And therefore, from this diagram, by taking a difference here and a difference here, I know how much is the potential. Potential inside my semiconductor here. What kind of a potential will it be? See, since the device is in equilibrium, it means I have not applied any voltage, right, to my system. But there is a potential inside it. So that's what we call as a built-in potential, potential inside the semiconductor here. Due to itself, because of change in doping and all that, there is a potential that develops inside the semiconductor, and that's the built-in potential here. All right. So we can know from here how much is the built-in potential here. We know the direction of electric field. We know it is in equilibrium. We know which one is P, which one is N. And once you know that, once you sketch, then also I'm sure you, for example, if I go into a region like this here, the electric field is 0. So drift current will be? Electric field is 0. So drift current, electron drift current, 0. Electron diffusion current, 0. Net current is 0, right? And same happens here also. But if I go somewhere here, what will happen? Where will be a drift current? Electron drift current. Electric field was in this direction, right? And so electron will tend to drift. Drift current will be in this direction, right? Drift current here. But it's equilibrium. So electron drift current will be cancelled by diffusion current. Can you all see the diffusion current? Where will electrons tend to diffuse? I have a high concentration of electrons here and lesser here. So electrons will try to diffuse to us from left to right here. So you can see all of those things from here, right? So there'll be a diffusion current here. There'll be a drift current here. Electron drift and diffusion current, they'll all cancel each other. Same thing will happen with holes also. Okay. All right. So far, we've talked about energy band diagram where we have one type of semiconductor, N-type or a P-type here. Let's look at, when you make a complete device, you have to attach metals to it. You have to apply a voltage. You have to carry a current to the external circuit. And let's see how we handle metal in an energy band diagram. So this is the picture that we have of a semiconductor. Semiconductor, we said that there is a valence band which is full and or a little bit empty because of holes here, and there's a conduction band here. And we represent the semiconductor then in a simple way by drawing this EC and EV only, right? The and in between the conduction and the valence band, we have a forbidden gap or the energy gap here. The simplified picture of a metal is like this here. I will have, just like I have series of bands below here, they're all full. In a metal also, I will have series of bands which are all full. But the picture in a metal is like this here. Note that like the topmost band here, if I go to, let's say, temperature equal to 0 Kelvin, okay, then this is the picture of a metal here. Completely full band and then completely empty over it. And in between is a forbidden gap. If I go to a metal, a simplified view of metal is completely full band here, but then the highest band is partially full. Okay, it's not empty. Note the difference here. It's not empty here. Now, if you recall, using some very simple calculations, we showed that a band which is completely full of electrons does not contribute to current. Okay, so in a semiconductor at 0 Kelvin, this will not contribute any current, and there are no electrons in this band, so obviously I will not get any current. So semiconductor at T equal to 0 will be an insulator, will not carry current. On the other hand, here, this band will not carry current, but this will carry current, is partially full. Okay, so a metal will keep on conducting, right? So that's the nature of the metal here. So you see that in a metal, all these electrons that are there here in this partially filled band are the ones which are of importance. They carry current. So I don't need to, in a metal, I don't need to take an electron, promote it to the conduction band, and thereby create an electron here and a helium. Electrons exist which can carry current right away. Okay, so the picture of metal is different. So when I want to sketch the energy band diagram of a metal, how should I do that? In a semiconductor, I sketch EC and I sketch EV and I show a Fermi energy. What should I do in this case? Does this band matter at all for us? It doesn't matter, right? It's always full. What matters is this particular band here, right? And so in a semiconductor, what would happen is at T equal to 0, where would the Fermi energy be? Can you see right? The highest energy level which is filled. Because what is Fermi energy? Fermi energy at T equal to 0, remember I drew a diagram of Fermi Dirac function which is abrupt, which means that all energy levels below EF are occupied, all energy levels above EF are empty. So the highest filled band that you see here, the highest filled energy level is where the EF is. Okay, that's where the EF is in a metal. Now, when you raise temperature, what happens is some electrons from here will go a little bit to a higher energy, and the probability of occupation is no longer sharp. That everything below EF is occupied, everything above EF is empty, is no longer sharp. There's a little bit of transition region. But as a first order approximation, you can say EF denotes the place where the highest occupied energy level inside my metal here. So the picture of metal that we draw is as follows here. See, this is the picture that of a semiconductor that we drew. EC, bottom of conduction band, EV, top of valence band, EI in the middle, EF somewhere in the, most of the time somewhere in the energy gap here. We had electron affinity and we had work function. These were the elements of energy band diagram of a semiconductor. In a metal, what do? All that I do is I draw an energy, which is the Fermi energy in the metal. What does this denote? It denotes that all energy levels below these are occupied and all energy levels above it are empty. So the only energy that I draw for a metal is EF. That's it. And vacuum level is there as usual. Now, what does phi m represent? Phi m is the work function of the metal. Is the amount of energy needed to pull an electron. There's an electron here, right at Fermi energy. To pull an electron from the Fermi energy to vacuum level outside, and that's called the work function of the metal. So the representation of the metal in an energy diagram is simply one line here that denotes the Fermi energy in a metal. And where is the Fermi energy in a metal? Well, with respect to the vacuum level, it is the work function. And for different metals, work functions are reasonably well defined. They do vary depending on the surface treatment, how clean the surface is and all that. But the work functions are very well defined. You can see here aluminum, the work function is 4.08 EV, electron volts here. Gold is 5.1, copper 4.7 here. So whichever metal you are taking now in an energy band diagram, what you can do is you can draw the vacuum level, and below vacuum level by 4.08 or 5.1 or 4.7, you can draw a level, and that's the Fermi energy in a metal. Okay, so that's a very simple representation of metal. And we know now the representation of a semiconductor. So all devices will consist of nothing but one or two or three more layers of semiconductors along with a metal on one side, a metal on the other side. And so we know how to represent each one of those. How to represent a semiconductor, how to represent a metal. Okay. All right, let's look at this picture then. I have two pieces of metal. You could think of two electrodes, right? Two electrodes here. And same metal, because I'm using the same color, it's the same metal here, let's say aluminum or copper. Okay. It is ground here. It is ground here. What does it mean? Actually, ground means that whenever I see a ground, what I'm saying is there's a connection between the two. Okay. There's a connection. Ground means basically through the ground there's a connection. What I imply is that there's a connection between the two metals. Okay. Both are identical metals. Note that there's no voltage applied. So in this, let's imagine that in between the two metals there's vacuum, right? Do you expect any field, any charges, any fields anywhere? Just two pieces of metal, that's it, right? A metal is neutral, a metal is neutral, both are neutral metals, both are identical, they're connected together. I don't expect any field or anything here, right? So vacuum level I draw. What is the vacuum level? Some arbitrary level. We are just saying, let's say it's taking as a reference. I'm saying the energy of an electron in this region is what is E0. Okay, that's the vacuum level. And we expect vacuum level to be, there's no reason for energy here to be different from here, to be different from here, to be different from here, right? There's no field, no potential, nothing. So why would energy be different anywhere? So that's why we draw an E0 flat throughout. This is in between the region here. Okay, no problem, E0. Now, how do I represent this particular metal? Well, this metal in energy band diagram will be represented by its Fermi energy, which is below the vacuum level by the work function phi m. Similarly, this metal will be denoted by a Fermi energy, which is below the vacuum level by phi m, which is the work function. Now note, I have said that the two metals are connected together. So the two when they are connected together, what does it mean? They're in equilibrium with each other. They're in thermal equilibrium, okay? And that's why I have a Fermi energy which is constant throughout. All right, so that's a simple picture that all of you can see for a two metals here, identical metals where they connected through a wire here. And that's how my system looks like. Okay? All right, so now let's add a little bit more complication here. Suppose I take now this metal and I add a negative potential. Okay, I add a negative potential here. I do this. Okay, again the two are connected together. Here through this wire here, they're connected together. But I add a negative potential here. Now, you can imagine what will a negative potential do. When I add a negative potential, what will happen to energies of electron here? With respect to the earlier case, what will happen? Remember, this diagram is what? This diagram is energy, potential energy. So when you add a negative potential here, what will happen to this metal's energies of the electron with respect to the earlier case? Will increase, because energy is what? Minus Q times V. Minus Q times, remember, it's electron. So that's why minus charge times V. And V is what? Minus 1 volt. So can you see that what will happen is the following. Look at this particular picture here. This part remains, we are saying, the same. Earlier as it was, wherever this was, this is here. Now this part, I have raised the energy of this particular, all the electrons by an amount which is equal to Q times 1. Right? So therefore, what does EF represent? EF represents the energy, right? So everything, all the energies are raised by an amount which is equal to 1 eV. Okay? Everybody agrees? This is as it is. This part, I applied a voltage of minus 1 volt and therefore I raised EF by an amount equal to 1 electron volt. I raised EF. EF represents what? Represents the energies of the electron. Okay? Alright, so the whole band here, I'm not showing the whole band will lift up by that much amount here. Okay, by 1 EV here. Now something interesting happens now. This is again vacuum here inside. What will happen now? You have 1 volt, minus 1 volt here, and you have 0 here. What will happen? It's vacuum here. What will happen here? Well, this will get charged, right? This will acquire this. You can see a capacitor, right? Metal. vacuum and metal here. So you can see a capacitor. What will happen? Charge here will be, can you all see there'll be a negative charge here? And there'll be a positive charge here. Right or wrong? Remember, it's connected together through the wire here. So there'll be negative charge here, there'll be positive charge here. There'll be a field here. There'll be field in this direction here because I have a voltage between these 2 points. So field has to be there. Now, remember, all this is vacuum level, right? Now, if there is a field, the voltage here is -1 and the voltage here is 0. What does, now when I said, remember there are many definitions of vacuum level here, of potential. One of them is psi equal to minus E naught by Q. So is everybody seeing that my vacuum level will now go like this here? You can see here, right here, see whatever is the energy of the electron here, right? As you go along the field, what will happen to the energy of the electron in the direction of the field? Can you see the energy will increase here? So can you see now the vacuum level is no longer flat. Vacuum level is going like this here. Vacuum level is what? The energy in this space here. So energy close to this particular metal here is still with respect to EF by phi m. The energy with respect to this is still with respect to phi m. But then the vacuum level is going like this here. All right. And note, potential is nothing but minus E naught by Q. So we know that there's a potential of 1 volt. So you can see that the vacuum level will also differ by 1 volt here. Because this point is phi m, this point is phi m. And if this has increased by 1 eV, the vacuum level will also increase by 1 eV. And I'm okay to draw it as a linear. Why? Because the field is constant. I expect a constant field, and note that field is nothing but derivative of potential with respect to x. So my E naught must vary linearly with x here. Okay. So note what happens when I take these two pieces of metal here and I just apply a -1 volt here. This one rises up. E naught goes here. This one stays as it is here. And then I know that here. Vacuum level, now note, must always be continuous. You can see why? E0 must be continuous because psi equal to minus E naught by Q. If there is any, just imagine, we are talking about a space in vacuum here, right? How can vacuum level is related to, or vacuum level is energy of the electron here? How can an energy of an electron, when you go here and then a little bit you go here, how can there be discontinuity? Discontinuity, energy here and an energy here, how can it be discontinuous? It's not possible, right? I don't have any charges or anything. So how can energy suddenly is one and then suddenly shoots up to some other value? It's not possible. So vacuum level is always continuous here. In this region here, vacuum level that we draw. So whenever we draw vacuum level in an energy diagram, is always continuous. There cannot be a discontinuity in vacuum level here. Okay, and the other way of saying it is E naught must be continuous. You can see here psi is minus E naught by Q. Whatever is the reference, we don't bother. The derivative of psi, which is nothing but derivative of E0, gives us the electric field here. I don't have any infinite electric field and all that. That's not possible. E0 is continuous throughout. Okay, this is an important point. What it's showing you several things. What happens to a metal when I apply a negative voltage? Is Fermi energy rises up, the whole Fermi energy rises up by an amount equal to the applied voltage here. See, this is rising up here. E0 is always from EF will be by phi m. Work functions, note that work function that I gave you value of 4.7 or 5, it doesn't change if you apply a voltage to a metal. Work function depends on the nature of the metal. You apply 5 volt, 10 volt, 15 volt, work function will never change. It will remain constant. Okay, so this phi m is a constant for us, this phi m is a constant for us. So now you can see how the energy diagram that is appearing here. Note, the system is no longer equilibrium. EF here and EF here, I can define an EF for this metal here, Fermi energy, which represents the highest occupied energy level here. But note, EF and EF are different here. Okay, the system is no longer equilibrium, which is okay. I've applied a voltage here. All right. So that's the picture. E equal to minus Q by psi and all that. Now let's look at another interesting cases. Now so far I've said the metals are the same, right? Now let's suppose I take two different metals. I take, for example, let's say this is gold. All right, this is gold, and this is, let's say, aluminum. Okay, gold's work function is close to 5 eV. Aluminum's work function is also close to 4. So roughly, let's say this is gold here and this is aluminum here. Okay, and now I want to draw the energy diagram. Okay, energy diagram of this. So what do I do? Two pieces of metal here, and note that I have not connected them up. Note, there's no connection here. This is not ground, this is not ground. Which means what? The two pieces of metals are isolated from each other. There's no connection, no relationship. There's no need for this to be in thermal equilibrium with this. It's a separate system, and this is a separate system. And they're isolated from each other. Now I want to draw the energy diagram of this. What is my starting point? If they're isolated from each other, what can I say about the vacuum level here? Is it going to be the same throughout? I don't expect any charge here. It's an ordinary piece of gold here, an ordinary piece of this thing. There's no charge, nothing. So it's the same vacuum level same. So I draw a vacuum level same here, E naught. Now where do I locate the Fermi energy of this one? I locate it 5 eV below. Right? Why? The work function is 5 eV. So the Fermi energy of this one is here, of this metal A is here, 5 eV below. Where do I locate the Fermi energy of this? 4 eV below here. Right? So is this energy band diagram clear? That's how it looks like. This is my metal A and this is my metal B. And vacuum level is constant throughout. Right? Now something interesting will happen. If I now put it to ground and put it to ground. Ground means what? I establish a connection. I establish a connection between them. All right, I establish a connection. So let's see. Let's do that. Now what will happen? Now what will happen? Take gold, take aluminum, separate them out, put it to ground, and so there's a connection between them. They are no longer isolated. Connection means what? They can exchange electrons. Right? Electrons can flow from here, electrons can flow from here. They can exchange now. They can exchange now, which means earlier there were two isolated systems. Now they are one system. And they'll be in thermal equilibrium. Its connection has been established here. Thermal equilibrium means what? One single EF. I can't draw two different EFs here. One single EF has to be there throughout the system now. Now remember, I had made the statement Fermi energy is nothing but chemical potential. It tells the direction in which a species wants, will move. Okay. I had also shown you this expression here. Remember, inside the semiconductor, I said the current can be written as N0 mu n del EF by del X here. What does this tell us here? If there is a gradient in EF, what is the direction in which the electrons tend to move? See, if there is a gradient, if let's say EF is higher at some place and lower at some place, what is the direction of the gradient? As I go from here to here, del EF by del X is positive. Correct? In some positive, which means current is positive. What is the direction of current flow? It's from here. So what happens is when you take these two metals here, what this expression is telling and what the definition of Fermi energy as a chemical potential, what it tells is that when you have a situation like this and you connect them up, electrons will tend to flow from regions of higher Fermi energy to regions of lower Fermi energy. They start flowing. They start flowing from here to here. Once you connect them up, electrons will flow from here to here. Higher Fermi energy to lower Fermi energy. It's just like, like a temperature difference denotes the direction of heat flow. And same, a Fermi, a difference in Fermi energy denotes the direction of electron flow. So electrons will start flowing from here to here. What will happen then? Let's say an electron flows from here to here. There'll be a positive charge here. And there'll be a negative charge here. And there'll be a positive charge here. As a result of that, what will happen to the potential? There'll be a potential difference between them. right? Internal potential difference. Can you see that this will start to come down? This will start to come down. Why? Because this will acquire, as you can see here, it must be bothering you, both are ground here. So after this thing, so what will happen is, I'll start getting a positive charge here, note, and I'll start getting a negative charge here. Because why? Because there's a Fermi energy difference between the two, and this gradient drives the electrons. It drives the electrons from B to A. How does it go? Well, I have a connection here. That's how it goes. Okay, from here to here it goes. So I get a positive charge here and I get a negative charge here. What happens then? I get a field here. Now, what does field represent now? Can E0 be constant throughout? Huh? So E0 will no longer be constant throughout. Can you see now, if this is the direction of the field, which E0 will be lower? Can you see that this will come down, this side of E0? And as it comes down, what happens? This EFB also comes down, right? Eventually, when thermal equilibrium is reached, where will EF be? It will line up with this one. It will line up with this one here, right? So this, you can see here, as the electrons go from B to A field develops here, and as a result of field, this side of the vacuum level starts to come down. And as it starts to come down, the Fermi energy, which is at a fixed energy level, it also starts to come down. As more charges go, this further comes down and down and down. And eventually what will happen? It will line up with this. Once it lines up with this, then I have no longer a gradient in Fermi energy. I've reached thermal equilibrium and my Fermi energy is constant throughout. Okay, everything stops then. All right, so that's the picture that is happening now. So once I achieve thermal equilibrium, then what I do is I draw a constant Fermi energy throughout. That's the first thing that I do. Okay, after thermal equilibrium. Then the next thing that I do is, at this side, I draw a 5 eV. Why 5 eV? Because that's the work function of metal here, and I know where the vacuum level is going to be here, right? Because vacuum level on A side will be 5 eV above, work function doesn't change. Similarly, so I know the vacuum level here, and I know the vacuum level here. I draw here 4 eV. Now, vacuum level, how will it go from here to here? It has to go in a linear manner because field is constant and it will be continuous. So I can draw the vacuum level. So I draw E0 here and I draw vacuum level like this. Okay. I draw a vacuum level here. Now note, I have not applied any voltage, right? There's no voltage applied. This is ground and this is ground here. But there is vacuum level here is lower and vacuum level up is higher here. What is potential? Minus E naught by Q. So how much is the potential difference between B and A now? Inside. Can you see that there's a potential difference here between these 2 points? How much will it be? So A, if I go inside, I'm not talking about now, forget about this point for a moment. I'm talking about if I look at here, very close here, then the potential here, psi A, minus potential here, very close to the metal here, psi B, is going to be minus 1 volt. Psi A minus psi B equal to minus 1 volt. Everybody sees that? You can see here, psi A is what? Minus E naught A at this particular point here. Minus E naught A by Q. And psi B is what? Minus E naught B by Q. And take the difference between the two. And so it tells us that there is a potential difference between the two here. But then, I'm sure it's bothering you. I have ground here, right? How do I take care of the fact that there's a ground here and there's a ground here? Well, why? This is sort of troubling. Why? Because I've only drawn a energy band diagram of this particular part here. Let me draw a complete, let's look at the whole system then. Not only this, because how will you connect it to ground? Let's say ground is nothing but a wire, right? So what have you connected then? Say this was gold, this was aluminum, and wire is, let's say, copper, right? So you've taken a copper wire and you've connected it here and then connected it here. What kind of so you have copper and a gold junction here, and you have a copper and aluminum junction here. Those two will be in equilibrium. Okay. So we'll see it in a minute. So the first point that I want to, let's see. mention to you is the following. What you are seeing is that I have a metal here and I have a metal here. When I connect the two metals up and they're in equilibrium, I have a difference in potential between them here. A potential difference forms between them. And that difference is called contact potential, because I've brought them into contact. I've not brought them into contact directly, but I've brought them into contact through a wire. They're still in contact, electrical contact, right? So whenever you bring two metals into contact, what happens is a contact potential develops. And how much is the contact potential? Well, let's see here. So you can see here the contact potential between two metals here, A and B, psi AB, is nothing but the work function of phi B minus the work function of A divided by Q. Okay, go back and see here. Psi between psi AB is nothing but the work function here and the work minus the work function here, because the Fermi energy is the same. Okay, so psi AB is nothing but phi B, work function of B minus work function of A, which is minus 1 volt here. All right, so that's the contact potential. Now, this is a very general statement. All that it is saying is the following. I've taken metal. Anytime you take two different materials and you bring them into thermal equilibrium with each other, there will be a potential difference between those two materials. How much will be the potential difference? The difference in the work functions divided by Q. Anytime you take any two different materials, you will have a contact potential. This is a very general result. I've shown you with metals. I can show you with anything. You know, the discussion doesn't depend on sort of metal. All right. So very, very general result. Two materials with two different work functions will always have a potential between them internal contact. And that's what we call as contact potential here. So now, if this is bothering you, let me show this here. So keep that result in mind. Work function, the potential difference between A and B is phi B minus phi A by Q. So I was showing you a ground like this and a ground like this here. All right. But what I mean by ground is nothing but that this is connected to this one here. So let's imagine I have metal A and metal B, and I connect them up. To connect them up electrically, I need another metal, right? So let's take, suppose I take a third metal C and I connect them up. All right. I take a third metal and now I've connected them up. Earlier, let's say A and B were isolated and I connect them up with the third metal C like this. Okay. Now, let's see what will happen now. What will happen between B and C? Can you see that there will be a contact potential between B and C? Anytime you put B and C will be in thermal equilibrium because you put them into contact. What will be the contact potential here? Remember, this psi AB, psi BC will be equal to phi of C minus phi of B divided by Q. So how much will it be? 0.5 volt. So there will be a voltage of 0.5 volt here. Drop here. All right. What about psi CA? Psi CA will be equal to, between here and here, psi CA will be equal to phi A minus phi C divided by Q equal to 0.5. Right? Because there will be a contact potential between them here. At this point, you put them into contact with each other. Now you go around the loop. You start from here. Psi AB is how much? Minus 1. You go around here. 0.5. And then you come back here and there's no inconsistency. You can see here. Psi AB plus psi BC plus psi A equal to 0. Okay? There's no inconsistency. When I say I'm putting it to ground, this is what I'm doing. I'm just connecting them up. That's all. By an electrical wire. Okay? And there is no problem. So earlier I was talking about only this part here, psi AB, and I was showing you that there's a contact potential. I was not explicitly, showing you, this thing here, but this is what it means here. Ground here. Now, see, so this is a metal here. I can say, let's say the potential of this particular metal is 0. Okay, I can take it as a reference that this is 0, right? So this is like a ground. 0 voltages, like a ground. I can just take the potential here as 0. So this is like ground. But then, as I go from ground to this junction here, there is a drop here. So there is no inconsistency. It's 0 here. But then at this junction, what happens? There is a voltage drop. There's a voltage drop. How much voltage drop? Well, C and A that you see here. There's a voltage drop. Voltage drop of 0.5 here. And this is the voltage drop at the contact here. And similarly, there's a voltage drop at the contact here because it's two different materials. There's another drop here. So many times in semiconductors and devices, what we are doing is we show it like this ground and ground here, and we talk about these parts here because that's where the interest is, right? And we show a potential difference. Just like I said, psi AB is equal to -1. So psi AB is -1, and then you see a ground here, and then you see a ground here, and you wonder, am I violating Kirchhoff's law, KVL? Well, I'm not violating because there are potential differences here, and there are potential difference here. We don't talk about it. Yes.
Is the wire that is connecting the two, work function is not in between these values.
Take any value, doesn't matter. Take any value. It will all add up because you can see, say phi b minus phi a, phi c minus phi b, and phi a minus phi c, whatever it is. Just add them up. Just add them up, phi b minus phi a, phi c minus phi b, and phi a minus phi c. It will all add up always to 0. It doesn't matter. Wherever it is. All right. So this is a very general, it's not about -1 and 0.5 or whatever. It doesn't matter. It's not about 4.5 or none of those things. All that it says is when you take two materials and you put them into contact, there is a contact potential. And the contact potential is equal to psi AB equal to phi B minus phi A. That's what it is. It's a very, very general result. And in fact, when you talk about PN junction and you say there's a built-in voltage. Built-in voltage is what? It's a contact potential between P-type and an N-type. That's what it is. P-type material is one, N-type material is another. You put them into contact, well, you'll get a contact potential. And that's what we call as built-in voltage here. So it's a very, very general result. You always have a contact potential when you put two materials in thermal equilibrium with each other. Okay. So again, remember now, again, at various places, we will show a diagram like this, ground and ground here. You will see internal potential. Don't wonder then, how come I have an internal potential? That internal potential is actually cancelled by a potential here and a potential here. Okay. And afterwards, we will not explicitly talk about these places here because my device is here, somewhere here, and these are regions of interest. Okay. So we will not talk explicitly about it, but it's understood that these are there and they balance the internal one. Okay. All right. So let's take this energy diagram here. Now that we know metal, how to handle metal here. So this is now interesting. I have a metal here. Metal on this side. I have oxide, silicon dioxide, which is an insulator. And I have silicon here. Okay. I have silicon here. Now look at this energy diagram. It shows you EC, EI, EF. It shows you E naught. It's a complete energy band diagram for you can see metal, oxide, semiconductor. So what is it, an energy band diagram of? MOS, right? We have not gone to MOS, but we are just saying, given an energy diagram, what all can we read from there? Okay, so it's all about what information can one get from an energy diagram here. All right. So system is in equilibrium, obviously. EF is constant throughout. Okay, what else can we see? What else can you get from here? Huh? Here you can see fields are 0, bands are flat. This looks like a P-type material, right? P-type material here because my EF is very close to EV or EF is below EI. So it's a P-type material here. But then as I travel from here to here, what is happening? Huh? What is happening? P, and then as you go here, is the whole concentration, what is happening to the whole concentration? EI is the difference between EI and EF is decreasing. So what is happening to the whole concentration? Decreasing. What would happen to the electron concentration? Can you see electron concentration will also, the EI is getting closer to EF. So electron is increasing. What happens at this point? EI equal to EF. What happens here? N equal to Ni e to the power EF minus EI by kT, right? If EF and EI are the same, the concentration at this point is Ni, intrinsic. And whole concentration is also intrinsic. Now when I come here, what happens? It is becoming N-type here. So we can see, and my material is starting. As I start from here, what happens is, the other way of saying EF is getting further and further away from EV is getting further and further away from EF. I'm getting depleted of holes. I have a lot of holes here, and my region is getting depleted of holes, right? Depleted of holes here. At this point, I have very little carriers. Ni is very small, right? 10 to the power 10 or so. Then as I get closer and closer, now my Fermi energy EC has become reasonably close to EF, and I'm starting to get an N-type material here. Okay? All right, so we can see this happening here, going from P-type to N-type in this case here. All right. Is the direction of energy diagram in the oxide consistent? All right, so let's think about this. What does the slope here denote? Slope of EC? Electric field, right? Should the slope here be the same as the slope here? I mean, I don't know how I've drawn, maybe, but should the slope here, the slope of this will also denote electric field? Oxide, we are modeling it as a very wide band gap semiconductor. So oxide also has a conduction band and a valence band, but with a huge energy gap. So it acts as an insulator. So the slope here denotes electric field here. The slope here denotes the electric field here. Will the two slopes be the same? Should be the same or not? Which law would you apply? What does Gauss's law tell us? Gauss's law tells us what? Epsilon 1 E1 equal to epsilon 2 E2. Unless there is a sheet of charge here or something. Right? So what you are saying is epsilon 1 E1 electric field here must be equal to epsilon 2 E2. Now the fact that the dielectric constant of dioxide will be different from dielectric constant of silicon, you will get a different slope here and a different slope here. Slopes will not be the same, because when you reach two different materials, there will be a discontinuity because of dielectric discontinuity here. So electric field here and electric fields here will be different. But note E0, can you see here? E0 will always be continuous here. E0 denotes, vacuum level will always be continuous. It denotes the potential. It denotes field, it denotes potential, and all of that there here. All right, suppose I give you some interesting things here. Say I give you, this is aluminum with a 4.2 work function. Okay, 4.2 work function. And I also give you, suppose I know in this part of the region here, P-type, we all recognize that this is P-type, and I give you what is the hole concentration. Okay, and how do I get hole concentration in this? If I know the level of doping, I know roughly the hole concentration is same as the level of doping. Once I know this P0, will I know this difference? Difference between EF and EV here? Will I know or not? P0 is equal to what? Ni, or another way of saying it is NV multiplied by EF minus EV by KT. So if I give you P0, you know where my Fermi energy is with respect to EV. So let's take a value here. Suppose I know P0 through doping, and I calculate this value, and it turns out to be 0.2 EV. Okay. Now note, is there a built-in voltage in this particular system? Is there a built-in voltage between metal and semiconductor? This is an equilibrium. This is my E0 here, and this is my E0 here. You can clearly see there's a built-in voltage here. How do I find this built-in voltage here? How much is the difference between here and here? Can I find that out? Just with the information that I've given you. What information? That I know my metals work function. I know my metals work function, and I know the doping on the other side. Do I know how much built-in voltage will form here? Well, how do I do that? Well, we do Kirchhoff's law. Kirchhoff's law applied on energy band diagram. Kirchhoff's law here, how do we go? Well, so this is the potential difference that we are talking about, right? Remember, what is potential? Psi equal to minus E0 by Q. So the difference between here and here is potential difference. Okay? Let's start here. This is here. So what we do is the following. Let's start from this particular point here. Okay, so I'm trying to find out what is the difference between the work function, these two here. Right? These two here. So I start from this region here and I go up. What is this energy increment? This will be equal to how much? So you see, in a Kirchhoff's voltage law, what do? You go around in a loop and you start adding up all the voltages, right? Here, what we do is we start from a point in Fermi energy here, and we'll go around and we come back to Fermi energy, back to the same energy, and we keep on adding, subtracting energy levels. The sum should be equal to 0 because we are starting from the same point, and we'll arrive at the same point here. So if we start from here and go up, how much is this energy here? Do we know that? See, from doping, we know this is 0.2 eV, right? What is the total from here to here? Eg is how much? 1.12. 1.12 is the energy gap of silicon. So 1.12 minus 0.2 is this energy, right? Okay, so you know that. Do I know from here to here how much is it? Not work function. From conduction band to E naught is what? Electron affinity. Electron affinity for silicon is how much? 4.05. So I know that. So can you see the following? What I'm doing is, as I go from here to here, that's equal to 1.12 minus 0.2. Correct? Then I go from here to here. Okay? Which is equal to 4.05. From here to here is this potential drop, right? This potential drop is what I'm calling as psi ms. Psi ms is what? The psi ms is the difference between metal and semiconductor potential difference. Psi ms is nothing but psi of metal minus psi of semiconductor. So that's the potential difference. So you come here then, right? That's minus psi ms. So I come here. Okay, I've arrived this by subtracting minus psi ms. I'm coming here. Okay. Now from here I come down to here, and then what do I do? I subtract minus 4.2, and that should be equal to 0. Right? So you start from some point here, go up all the way here, come down here, and then come here and come back here, and you add it up and you get what? Psi ms equal to 0.77. So I know now so all that I required was something very simple. All that I needed to know was how much is the metal's work function, 4.2 eV, and what is the level of doping here through which I knew 0.2 eV here. And then I know what is the total voltage difference between. So what it is saying is the metal is at a higher potential compared to semiconductor by 0.77 volt. Okay. Can you all see that metal is at higher potential than semiconductor? Remember, keep this in mind. Potential is minus of energy. Okay. So this E naught is lower than this E naught, which actually means that this potential is higher than this potential here. By how much? By 0.77 eV. How has this potential come about? What is this potential? This is the internal built-in potential, because note that Fermi energy is same everywhere. I've not applied anything. So it's the internal potential difference inside a MOS system here. And we can very easily calculate now. Given here and given this, we have shown how to calculate the potential difference that is there inside my MOS system. Okay. So let's stop here. We'll continue in the next lecture.